One of the biggest challenges we face today is energy. We use a lot of energy, and most of it comes from burning fossil fuels. In fact, about 85% of the global energy consumed comes from fossil fuels, which is oil, coal and gas. We know that burning these fossil fuels produces large volumes of CO2, which is being released into the atmosphere, damaging the environment.
And we know that releasing carbon dioxide runs a significant risk of man-made climate change.
The problem is compounded by the fact that demand for energy grows globally by about 2% each year. It's likely that over the next few decades we're going to continue using large amounts of fossil fuels to meet a good part of the energy demand.
So to respond to global warming, either we need an energy supply that has no carbon release, or we need to find ways to use less energy.
One form of sustainable, low-carbon energy is wind power. Wind power in the last 25 years has developed into a major source of electrical power generation, already generating several percent of the world's total electricity output, and in many countries it's the fastest growing form of electrical power generation. Wind turbine equipment is becoming cheaper, it's becoming more reliable, and we've learnt how to integrate wind power effectively into a grid. Onshore wind farms are now approaching the point of being economical without subsidy, which is very good for the industry. We've got to think very carefully where we put our wind turbines. Clearly there are areas of great beauty where the landscape simply cannot accommodate wind turbines. Nevertheless, we want to generate low carbon power, and so we have to make some compromises. We have to find enough sites to generate the power we need. A further issue is that the wind is variable. At the moment, the variation in output is easily accommodated within the normal operation of a grid. However, if we look into the future where a very large proportion of our power might come from wind, then we've got to think of some way of electricity storage to even the output. One way round the difficulty of finding enough suitable sites on land is to build wind farms offshore. The attraction is there's more wind offshore and there's a lot more space. The problem is that, to date, they're considerably more expensive. If we can find a way of putting them offshore at reasonable cost, then we can harvest a lot more energy. Our research at the university has been very much focused on trying to reduce the cost of wind turbine equipment and increase reliability. Specifically, we're working on the generator. Most contemporary wind turbines use a form of generator which relies on carbon brushes to make contact to its moving part. These are a known reliability issue and they add to the cost of the generator. We're working on a new type of generator which doesn't have brushes and thereby eliminates these problems. So our technology could well be a cheaper and more effective approach. We've got to remember that electricity only accounts for about 1/3 of our total energy consumption. So what we must think about is whether other energy usage, such as home heating or transport, can be transferred to electric supply, and then we can of course generate that electricity cleanly. This would be a good way of reducing CO2 emissions. Although at present, wind power accounts for only about 1% of overall global energy production, it is growing rapidly, and I think in the foreseeable future that it will become a major producer of low carbon energy.
Most of the world's electricity is derived from coal and gas-fired power stations. About a quarter of the world's carbon dioxide emissions come from the burning of coal. In order to reduce the emissions of carbon dioxide at coal-fired power stations, it's possible to use carbon capture and storage, or CCS. This is a technology in which carbon dioxide is removed from the waste gas produced by the burning of the coal and is then stored deep underground. Once the carbon dioxide is captured from the exhaust gas, it's then compressed and turned into a high pressure liquid which is pumped a couple of miles underground. In the rock, it spreads out between the grains, rather like fluid moving through a sponge. Our research is aimed at looking at how the carbon dioxide spreads through these subsurface storage sites. We've been looking at the flow of carbon dioxide on the scale of the grains in the rock, looking at the effects of surface tension. We've then been looking at the flow on larger scales as the CO2 moves through the sandstone beds. We've also been interested in understanding the effect of layers of clay, which can cause the CO2 to spread out in unusual ways. There are projects where CO2 is being injected into large subsurface reservoirs. There's one in the Norwegian North Sea and one in southern Algeria in the Sahara Desert. At each of these sites, about 1 million cubic metres of CO2 is being injected every year into the subsurface, and we're using some of our models to try to understand the observations being collected at each of these locations. There are risks associated with storing CO2 when assessing the potential for CO2 to remain trapped for thousands of years. There are potential for slow leakage to the surface, or in the event of geological events such as earthquakes, more dramatic release to the surface. Understanding these processes helps to minimise the risks of leakage. One of the main challenges is to create a commercial environment in which it's economically viable to build large CCS projects. Over the last 10 years there's been an enormous advance in our understanding of CCS. However, we're now at a stage where many more large-scale demonstration projects are needed to learn about the practical challenges of the engineering involved in CCS. Fossil fuels are likely to be a major part of the energy supply system for several decades to come, and our work on CCS, as well as the pilot plants and other research around the world, suggests CCS can have a major role in reducing CO2 emissions associated with these fossil fuels.
It would be great if we could find a solution to the energy and emissions problem on the supply side, but it's difficult. There are no easy solutions for a carbon-free energy system, so we have to look at demand as well. And the great news is that there are a lot of opportunities for using less energy. In buildings, we can use less energy because we can build well-insulated, sealed houses, and we know how to do that. For cars, we can make lightweight cars that use much less energy. The current world record for cars is 14,000 miles per gallon, compared to just 35 on average in the UK at the moment. But the challenge that we're looking at here is about the industry sector. The largest amount of energy is used in industry. 36% of the world's energy is used in industry, and it's amazingly efficient already. Over half of industrial energy is used to make just 5 materials: steel, cement, paper, plastic and aluminium. And those industries have paid heavily for energy for 100 years, so they're using it efficiently because they're already motivated to do so. So if we can't make them with less energy, the implication is that we have to use less new material. And that's what's driving us here. It turns out there are many ways that we can use less material without any real economic pain. A simple example is that new office buildings put up in European cities at the moment are designed for 100 years but typically replaced after just 40. If we could keep them for 100 or 500 years as we do here in Cambridge, then we'd be able to reduce the total amount of material required to provide offices and accommodation. Using things for longer is great. In many cases, we could make them lighter weight. Most buildings, we've found, could use 1/3 less material with no loss of performance whatsoever, just if we made them more precisely. Equally, we could use goods more intensively. We know that in the UK, we've got 1 car for every 2 people. We drive it for 4 hours per week, and it only has 1.5 people in it. So if we use fewer cars more intensively, we'd need less material, and of course as a benefit we'd use less petrol and therefore emit less carbon. All new office buildings are made with columns and beams. The horizontal beams are typically a constant depth all the way across the building. But actually they shouldn't be. They should be deeper in the middle and less deep at the edges. And if we made them like that, we could use about a third less steel with no loss of performance. So one of the things we've been working on in the lab is to invent a new process for making variable depth beams. When the buildings are taken down at the end of their life, at the moment we demolish them. But if we instead deconstructed them, the steel in old buildings is perfectly ready to be used again. So we could unbolt the old steel frame, clean up the steel, and then use it in a new building. So there's a whole range of strategies for using less material without any significant reduction in the service that we take from having that material around. We make materials so efficiently that they're cheap, and that means that we've developed an economy where we assume that we can use materials abundantly. We need to move into a different system now. So our work has been to try to find ways to live with less new material, and perhaps to our surprise we found there are a whole range of options for doing so, and now we're working with businesses and with policymakers to try to bring that about in reality.
Ultimately, it comes down to how seriously we see the threat of man-made climate change. If we do see it as a serious threat, as many of us do, then we must look at significant reductions in CO2 emissions.
And that means a big change to our energy system, and that could be on the supply side or the demand side.
Over the longer term, the energy supply will evolve towards alternative sources of energy, including solar, wind, hydro, geothermal, biofuels and nuclear, and there are exciting opportunities for innovation in new energy technologies.
All, or at least many of these, have a role to play, but they need to be assessed against local conditions.
Technology such as CCS provides a means of reducing the CO2 emissions associated with burning these fossil fuels as we transform the energy supply system to renewable energy.
On the demand side, what we've seen is that we can use a lot less energy without much loss of service, but doing so does require behaviour change. That's where the debate now is. On the supply side, we could do technology and policy, and on the demand side, we can do behaviour change.
Despite considerable financial and technical difficulties, I believe if we're going to avoid the significant risks of man-made climate change, that we must continue to pursue the development of low-carbon technologies.